All right, ladies and gentlemen, welcome to 10.1, the beginning of our study of calculus. Uh, as you recall, we went over a little bit of this today, the previous day in class itself. But what I want to do now is just kind of go through a couple more examples and kind of talk about other little things, such as you see here, the derivative and tangent lines and that sort of stuff there. So historically, this problem comes down to a very basic problem that this guy Galileo did in his house, basically saying that if you rolled a ball down a hill of uniform slope, you could actually calculate the average velocity. The average velocity is not too hard in the fact that average velocity is just the change in distance, which is 16 over the change in time. And 16 over 4 is pretty easy. It's just 4 feet per second. And that's the average velocity. That's basically what the ball averaged as it was moving. Now that's pretty straightforward, pretty easy. But then what ended up being the question, as I was kind of mentioning in class, is what would be the instantaneous velocity at 3 seconds after you rolled the ball? Well, Galileo was struggling with this because he knew that velocity is the change in position. So you have to understand that S is position, T is time here. He knew that velocity was the change in position over change in time. But what his problem was that instantaneous velocity meant that time was not changing. And so if time was not changing, delta t would be 0. And that's no change in time. So therefore, it's an impossible question to answer. But like I was mentioning, he was strictly, all he could use was some algebra and geometry, because it's really all he had at his point in time. Calculus didn't come till later. So he couldn't do it. But that's why the other guys had to come in, Newton and Leibniz and stuff like that. Now, if we went back to this ball and we said, okay, we could say the ball's distance s after t seconds is exactly t squared feet. And he actually proved this, Galileo did. He proved that as the ball rolled down the hill, after t seconds, it went t squared feet. So after 4 seconds, it went 16 feet. After 10 seconds, it went 20 feet. And he calculated this, and he actually got it out pretty well. And we can do what we did the other day with instantaneous velocity at 3 seconds just by thinking about the secant lines, or the average velocities, as we got closer and closer to 3. Now, I've done this already here. So if we wanted to go from 3 to 3.1, this would get pretty close. And we'd get an average velocity of 6.1. And like we kind of continued that the other day, we said, okay, well, what if I got that distance closer together? We would get something around 6.05. And very basically, we would probably figure this out, just like we figured it out on the CFA example that we did. We would figure out that the instantaneous velocity, as t is getting closer and closer to 3, as that gap is getting closer and closer to 0, then it would be 6. Very easily found that, okay, yeah, we keep getting closer and closer and closer, we get it closer to 6. So that's kind of a recap over what we did on that CFA example, only in a real world kind of sense. So what we want to go into what we were really kind of diving into in class itself, and that is this idea of tangent lines. So this is a line that touches a curve at exactly one point, or it kind of bounces off that point. And I do want to take note of this. If we were to have a cubic function like so, draw this off to the side if you want to draw this. People get a little bit confused when we say a line that touches the curve at exactly one point. Because if I was to think about the tangent line at this point, and we looked at this tangent line, and it came down here, and it touched, and it went through, it only touches at that one point. But then people confuse themselves and go, oh, well, it touches over here as well, so there is no tangent line. But there is, and we really only care about locality. It's really, we only care about this local point right here. We don't really care what's happening anywhere else, just at that point. So this still does have a tangent right here. And it has a tangent right here as well, a different tangent, where somewhere over here it will intersect again, but that point doesn't matter. Only this tangent line in this little box right there is really what we care about. All right, you'll see those type of examples a little bit later. So if we wanted to look at the tangent line at the point x equals 3 on the curve y equals x squared, and that goes back to the ball problem. So we get our quadratic here, and this is just the function x squared, and at the point 3, 9, we could calculate this out approximately. If you approximated this using just lines and stuff like that, you would get 6, and it turns out the slope of the tangent line is the instantaneous velocity of the function at 6, which means the slope of the tangent line at x equals 3 is 6, and vice versa. We can say that means that the instantaneous velocity is at x. That is the instantaneous velocity at x equals 3. So let's get to the calculations that we were talking about this morning. The derivative at a point. So here we get our kind of formal definition. The derivative of a function f at x equals a is denoted by this new stuff for you. And this is said f prime of a. And the prime notation is that little apostrophe there. But what that represents to us is the derivative of f at a. So this is your very first, outside of the word limit, this is probably your biggest calculus word to date right now. And that's the derivative at a point, the derivative itself. And this is the limit that we talked about in class. This is the derivative at a is defined by the limit as h approaches 0 of f of a plus h minus f of a all over h. And you got to remember, what we talked about in class was that was really looking at a secant line between a and a plus h, because the distance between there is h. This is the coordinate a comma f of a, and this is a plus h and f of a plus h. And we can find the slope between those 2 points, and we would say, okay, as this distance between the two x values becomes 0, what is happening to the slope? We'll notice that the slope starts getting steeper and steeper and steeper, closing in on this first value here. Now, there are times where the derivative does not exist. So we can have things where it's a non-continuous graph where there might be a jump or a hole. We could have things with corners, like absolute value functions. These right here are going to be a couple examples of functions that are not they're not differentiable at certain values for a, and that would be absolute values, cube roots, and piecewise functions. Okay, so your absolute value function is this. You can find the derivative at every single point except that vertex. For cube roots actually look like this. Oops, drew it wrong. I even drew this wrong. Technically, it comes in here like this and gets really steep. So steep that it's basically a vertical line, and vertical lines have no slope, and therefore we can't do it at that particular point. And then piecewise functions are just ones that we can right with a whole bunch of non-continuous pieces, we can draw a thing like this. It comes up here, and it comes up here, and then it does this, and then it does this. That's a pretty ugly one. But we can find the slope at every point except for these two right here. Couldn't do that. And what we're trying to basically say here, anything without a well-defined slope. Well-defined means you can actually find it. I can't find the slope here at some of these points. All right, so what I want to do now is, like we did in class, is I want to do a couple problems. Oops. There are a couple ways that this can be asked, so you need to be able to be familiar with every way that this question can be asked. The first way is find the slope of the tangent line at x equals a. Or it can say find the slope of the tangent line at the point a comma b. But it means the same thing. The other way is to say find the derivative of the function at x equals a. So slope of the tangent line and derivative are going to mean basically the same thing here. So here we go. This is also kind of a way this can be said in shorthand. F prime of 4. So I need to find f prime of 4. So that is finding the slope of the tangent line at the point x equals 4. So we need to do our process, and this is what we are going over today in that one example. So we need to do the limit as h approaches 0 of, that's the f of a plus h. So it's going to be 2 times a plus h squared minus 3. Oops, sorry, not a. A is 4 in this case. A is 4. So let me change this to blue. A is 4. Get that back to red. And then minus f of 4. And f of 4 in this case is 16 times 2 is 32. Minus 3 is 29. All over h. And like we did in class, we need to simplify this statement. 2 times 4 plus h squared. So I got to FOIL. 4 times 4 is 16 times 2 is 32. 4 times h plus 4 times h times 2 is going to be 8 times 2, which is 16. And h squared times 2 is 2h squared. Minus 3 minus 29 all over h. And the limit as h approaches 0 of, okay, so now we need to simplify some more. 32 minus 3 is 29. Minus 29 is 0. And again, we get that nice little thing there. That was supposed to be squared. And we get 16h plus 2h squared over h. And here again, this is where that interesting piece comes in and goes, oh, well, h is not 0, so I can cancel this stuff out and say I get the limit as h approaches 0 of 16 plus 2h. And now I just say, okay, as h gets so close to 0, this thing just goes to 0. It basically becomes 0. And therefore, the slope of the tangent line at x equals 4 is equal to 16. I think I have one more example here. I do. So same idea. Notice I'm going to give you guys a lot of quadratics, a lot of radicals, and a lot of rational functions. So we're starting here with just quadratics. So I need to do the same thing. I need to say, okay, it's the limit as h approaches 0 of, I need to plug in 2 plus h squared minus 2 times 2 plus h plus 1 minus whatever f of 2 is. So I get 4 minus 4 is 0 plus 1 is 1 all over h. I'm going to come to this side here. And now I get to do some algebra 2 again. And I get to simplify. 2 plus h squared becomes 4 plus 4h plus h squared minus 4 minus 2h plus 1 minus 1 all over h. Which then, again, simplifying, 4 minus 4 is 0. 1 plus minus 1 is 0. And I get an h squared plus 2h all over h, which is then equal to limit as h approaches 0 of h plus 2. And now all I have to do is, now that I've simplified this using all of my Algebra 2 concepts, all of my Algebra 2 knowledge, I use a little bit of calculus to say, okay, as h goes to 0, this thing gets so close to 0 that it's basically 0. And my answer is 2, and 2 is equal to the slope of the tangent line at x equals 2. Oops. There we go. All right, what if we wanted to find an equation that could calculate the slope of every point, or the slope of every tangent line at every point on a function? Well, that's what the derivative is. The derivative function is actually a function with respect to x, and we can do the same limit, only in this case, instead of an a, we have an x. So we're going to leave it as a function, and we're going to have a function as an answer. And as I was just saying, what this is it will be a function that we could just plug numbers into, and we can calculate the slope of every tangent line at every point on the original function f. That's pretty handy. Now, this does only work for values of x where the limit exists. There's certain little things that are going to come up a little bit later, but right now let's just look at the basics. You do need to understand that f prime, in this case, when we talk about derivatives, can be written as, instead of f prime, it can be written as dy dx, which really kind of comes from change in y over change in x, because you have to understand that derivatives just mean slope. So dy dx kind of comes from delta y delta x, and so we're really just thinking about slopes here. So whenever they say dy dx means take the derivative of y with respect to x. We'll get to more of the with respect to a little bit later. So what I want to do is I want to find the derivative of x squared. And we're going to use this statement from up above here. And we're going to say, okay, it's the limit as h approaches 0 of f of x plus h. So it becomes x plus h squared minus f of x. Well, f of x is just x squared. And notice we're not going to get a number all over h. And this thing squared gets me an x squared plus 2xh or hx plus h squared minus x squared all over h. We keep this process going just like we did before. And x squared minus x squared is 0. And I get 2hx plus h squared over h. Again, everything canceled so we can, everything disappeared so we can cancel some h's. This becomes a 2x plus h. And then we say, okay, what happens as h approaches 0? As h goes to 0, this thing goes to 0. So I get the answer of 2x is equal to f prime at x. It's the derivative of the function itself. And if you want to think about this, this problem was the problem we dealt with the ball rolling down the hill. The function was x squared. And we wanted to know what was the derivative. What was f prime at 3? What was the slope of the tangent line at x equals 3? Well, if I have an f prime, I can just plug it in, and that's going to be 2 times 3, which is 6. And if you recall, that's actually what we figured out from just a couple secant lines. So we can use the derivative function to find the slope at whatever value we want. Oops. Okay, there we go. Now let's try one here. If I give you the function y equals 1 over x, and I wanted to find dy dx of 1 over x. So this is what we call a reciprocal function. This is kind of a harder problem because it deals with fractions and fractions. But we can still do this. We can say, okay, dy dx is equal to the limit as h approaches 0 of f of x plus h. So we would say, okay, this is 1 over x plus h minus 1 over x divided by h. All right, bear with me here. We got limit as h approaches 0. Well, in order to do this problem, we need common denominators. And we do some common denominators here. We're going to multiply by x over x. Now we're going to multiply here by x plus h over x plus h. And we get a little bit of stuff here. So we get x over x times x plus h minus x plus h over x times x plus h, and it's all over h. Okay, so I'm going to move all the way over here to the left. I'm going to say this is equal to the limit as h approaches 0 of, I have common denominators here, so x minus x becomes 0. 0 minus h becomes a negative h, all over x times x plus h all over h. Now, if you remember, one of my little tricks here is we're dividing by h, so it's actually meaning we're multiplying by 1 over h, and the h's cancel. We're left with the limit as h approaches 0 of negative 1 over, well, x times x plus h. And then as h goes to 0, this becomes negative 1 over, this x plus h is actually x plus 0, so it's x times x is x squared. This is dy dx. Now, if you recall, on that CFA, the 1 over x was actually one of your problems, and you wanted to find the slope of the tangent line at x equals 4. And if I plug this in, 4 squared is 16. I get negative 1 over 16, and that is actually the answer that you would have gotten had you had the correct process to begin with. So the slope of the tangent line at x equals 4 is negative 1 over 16, which is negative 0.0625. All right, so here is the first part of our assignment from Chapter 10, page 803, 1 through 14, and 23 through 32. All right, I hope you guys have some fun with this. This is a pretty, I love doing this stuff, and I will see you guys tomorrow.